Hello and welcome to another Earth Science podcast. I'm your host, Mr. Buss, and this podcast we'll be talking about Earth's oceans. In our conversations on climate, we'd previously been discussing atmosphere's role on moderating the Earth's temperature, and now let's get into a discussion on water and the fact that the Earth is covered in water. 71% of the Earth's surface is covered with water, and water has a very high specific heat, which means that basically it takes a lot of energy to heat water, and once heated, it gives off a lot of energy. So as air blows over the oceans, the air either cools if the oceans are warm or warms if the oceans are relatively warmer than the air. So in effect, the oceans act as just a giant heat sink, just containing a lot of heat energy and dispersing a lot of heat energy throughout the planet. Now, you've seen this slide already in one of our atmosphere podcasts or screencasts. It's just worth bringing up one more time, in that Earth is not the closest planet to the Sun by far. Mercury, then Venus, then Earth, then Mars, and so on. And then you get your gas giants. But again, some places on Earth get as cold as -70 and others as hot as 55. The range is 125 degrees Celsius. On Mercury, it's a much greater temperature range difference. And again, the Earth's atmosphere and Earth's oceans play a role in keeping our range in a comfortable level as opposed to what you see on Mercury. And now it's almost better to think of the oceans as just gigantic rivers than stationary bodies of water like a lake or so on. Let's draw the equator in here, and I don't know, I didn't draw a great equator there, but you get the idea. So there's the Earth's equator, and in the northern hemisphere, basically are getting clockwise rotations, and think of that as a river of current flowing and clockwise. And in the southern hemisphere, you get counterclockwise rotation in the ocean gyres. All right, so basically near the equator, you're getting obviously the most direct sunlight, so you're heating the ocean the most at the equator, and then that heat energy is transferred in the gyre, and the gyre brings it in the northern hemisphere to the north, and so the warm water flows to the north, and then the cold water flows back to the south, and that's the northern hemisphere. In the southern hemisphere, the water then deflects southerly to the South Pole and cools, and then comes back up to the equator. So these ocean gyres are critical in dispersing heat energy from the equator to the poles, much like atmospheric circulation in the Hadley cell brought warm air from the equator to the poles, or at least to the Ferrel cell. All right, so if we zoom in right here, we get a closer look at a thermal image here of the Gulf Stream, which just really illustrates the idea that there's a current in the ocean, and it's almost like a river as opposed to a lake or a stationary body of water. So now we're going to add a level of complexity. Not only are there surface currents with those gyres that we looked at, but also there are deep water currents as well. So downwelling is where you actually, when you take a surface current and drop it down to the bottom of the ocean. All right, so why would it do that? Well, as water travels to the poles, it becomes more dense because it becomes cooler. So obviously as water traveled from the equator, it becomes cooler. That makes it more dense. And it could also get saltier based on evaporation. As air evaporates water out of the ocean, salt remains. And so as water travels from the equator north or south, it's going to become saltier, and also that makes it heavier. So when it gets to a critical point, it sinks, and that's called downwelling. So there's various places on the planet where downwelling occurs, and it will then travel to the bottom of the ocean basin and then begin basically a current that is scraping along the bottom of the ocean. All right, so obviously water has to upwell, and so as the deep ocean currents, as the water scrapes along the bottom of the ocean, at certain places it's going to be brought back up to the surface. Various reasons. Trade winds, basically winds blow along the coast, blow the surface water away, and deep water is brought up. And this is vastly important because the water that had been traveling along the bottom of the oceans was picking up a lot of nutrients from organic matter that might have settled and settled to the bottom of the ocean, carrying with it nutrients. Those nutrients then were picked up by those cold water formations and then brought back up, and plankton are going to use that near the equator because a lot of upwelling can occur near the equator. And so sunlight at the equator plus the nutrients brought up from the deep is going to be the start of the food web, which even we depend on as fishing industry and so on. This is just illustrating upwelling as wind blows along the coast. The surface water moves away and is replaced by water from the deep. And again, that water is nutrient rich, so vastly important for food webs in the ocean and even on land. Right, so not a form of heat energy, obviously, but wave energy is a form of energy that travels in the oceans. So waves are caused by wind, and to get a bigger wave, you're going to need a greater wind speed blowing across the ocean. You're also going to need a longer duration, so the wind has to blow more than just 15 minutes. It has to blow maybe for several days. And fetch is how much ocean is it blowing across. So those three things: wind speed, how long is it blowing, duration, and fetch, the amount of ocean, gives you bigger waves. So wave energy is a shallow water phenomenon. The wave energy doesn't travel very deep. And then as the waves come crashing into the shore, they're going to start flattening out and becoming more of an oval appearance for the water molecules until eventually the wave's going to crash down. Well, I think we'll call it good, and thanks for joining us, and I'll see you next time.